Thank you for the opportunity to speak here. So I thought I start my presentation with a picture of the CWI, which is a Math and Computer Science Institute here in Amsterdam on the other side of the water. And I did my PhD there, but it's also the place where Python was born in the late 80s. So I thought that's maybe a nice way to start. And to warm you up a bit, I thought let's start with a small Python quiz. I hope you can see it at the back, because I was in a different talk and I was completely standing at the back and I couldn't see the font, but assuming, well, at least the people that can read the font size, the question here is, if you execute those statements, what is y then after executing that third statement? Please raise your hand if you think it's answers A, if it's the empty set. So I see some hands there. And then please raise your hand if you think it's answer B. Also see some hands there. And who didn't raise his or her hand a single time? Also some hands. I think in this case it is answer B. So because Y was not changed by that last action. And now the second question, it's a totally different question. If I define the function like that, and then I call that function, maybe you need some time to parse what is on the screen. So if I define that function and I call it, then I get that answer, the list of 1. And now if I call that function again, the question is, what output do you get? Who thinks that it's answer A, that you get the same result? And now who thinks it's answer B? I think slightly more people, and here the majority is right. That's actually answer B. All right, now that we have talked about Python, I'm going to switch topics and actually go to the actual topic of my presentation, which is about data ecosystems. And what is a data ecosystem? Let's start by defining that. I looked up on Google and I found this definition. Data ecosystem describes a group of organizations working together to share data for reasons of mutual commercial interest or social good. Well, this is one definition. You can get other definitions. For example, McKinsey talks about a data ecosystem is a platform that combines data from numerous providers and builds value through the usage of processed data. So it's, in other words, like a similar definition as the one from this Zulk company. And then I added the third line that you can actually also have a data ecosystem in a large company, right? That there's multiple business units in the large company that are collaborating on data and each have maybe live in their own jurisdiction, or in other way they are separated and form independent groups. So it gets interesting if those data ecosystems are trying to collaborate on data that is sensitive. So what do I mean by sensitive data? Can be healthcare data, your medical records. Think of a collaboration between, say, a hospital and your health insurer, and you don't want that the hospital just hands over all the data to the health insurer to play with that. Or it can be government data, your basisregistratie personen in Dutch, like the registration of who you are at the local municipality. But also in manufacturing, you can think of confidential data. For example, how should I make this chip that is coming out of the factory? And that's my trade secret, so that's more IP-related data, intellectual property. Or finance, think of your transaction data. You don't want that to be just in the public. That's private data. And if there's this sensitive data involved in these data collaborations and these data ecosystems, then you get often that the bottleneck is sharing data. So everybody from the start was willing to collaborate, but then actually when it's the moment to share this data, then everybody is a bit scared because people ask themselves the question, maybe I close a bit the door here because I hear the other talk myself. How to keep this multi-stakeholder data safe in such a data ecosystem. So how do we safeguard the confidentiality of the data? And that can be because you are worrying about, say, the curious individual's problem, curious employees or system administrators, or maybe there can be security problems at the cloud where you are hosting your compute or storage, or think of the accidental disclosure of third-party data. So, for example, you are in this data collaboration, you're a data scientist from organization A, and you're working with the data from this other organization B, and then, oops, you make a mistake and you leak the data to the internet. Then yeah, you have to call them and say sorry. And then you have a problem. So people worry about these scenarios. And also, for example, this first one, this curious individual scenario, there was recently in the Dutch press this news item about Bunk, which is a Dutch bank, and their employees were secretly looking into the accounts of, for example, ex-lovers. And that's, of course, not something that you want as the management of this bank or as a user of this bank services. Another aspect which is important here is purpose binding. So maybe somebody in this data ecosystem is willing to share a data set with the consortium, but only for a given purpose. And for that purpose, you have maybe looked in the law that this is a lawful processing, but you don't want that this same data set is used for all kinds of other purposes, right? Function creep, that is sometimes called. And also, another important theme is so-called data minimization. So if you are processing data, you actually want to reveal the minimum amount of data that is needed for this use case. You don't want to reveal more data that is actually not relevant. And ideally, if you're going to run a computation, then you want to keep the inputs to that computation private and only reveal the result. And sometimes I depict that in this way as a funnel with a big opening at the top where a lot of data is going in, and maybe the computational result or the result of your data analysis is just this single number or these few numbers that are coming out at the bottom end of the funnel, and only that you want to reveal, and you ideally want to keep the rest private. So, well, I'm from the company Roseman Labs, and we claim that we have a solution for this problem. And the tagline is extract insights from data that you cannot see. And now, yeah, you might wonder, yeah, how does that work then? So let me try to explain what type of product we have and how that can solve the problems that I just talked about. And I will explain that by first showing you the system topology of what we have and then explain the major or the important properties of that system. So here, I'm not sure if I have a laser pointer here in this. I have. Not sure if the laser pointer is also visible at the back, but here there's a client or maybe another client, and those clients, they could upload data in the system, but the data is uploaded in such a way that it's encrypted. And it's encrypted in a special way Namely, it's encrypted and ends up at several computers. So it's split in a special way. It's called secret sharing. But I cannot, with the time here in the talk that I have, I cannot precisely explain how that works. But you should view it as a form of distributed encryption. So encrypted data is coming into the system, and then those servers here in the middle, they are in the cloud, and they can jointly run computations. And if the security assumption holds, namely that there is no collusion between these servers, in normal terms, that means that those servers, they run, for example, in different clouds, and they are administered by different people, right? That do not collude together. Then you have very strong guarantees, namely that none of these servers individually sees any data that is being processed. And also, the clients, they can only run queries. I was just talking about the role of the client from uploading data, but the client can also initiate queries to run on that uploaded data, which can come from several parties. And these clients, they can only perform queries that have been authorized. And then you can ask by whom? Well, there's some delegate of this data ecosystem that has the power to acknowledge or to approve queries. And that's then, of course, a different person than the person who initiates the query. So this is the system topology of our product and also the guarantees. And this MPC stands for Multi-Party Computation, and that I'm going to try to explain in a few slides, also on a very high level. And I start by explaining what it is not. So it's kind of the opposite of involving a trusted party. Because involving a trusted party is kind of an existing solution also for this problem, that you hire some company that you fully trust, you copy all the data to that company is going to run the computation and then send the results back to the consortium or to this ecosystem. But then you have to fully trust that trusted party, it's in a name, and also if there is a curious employee in that trusted party, or the trusted party makes a mistake and leaks the data by accident, then there is again that problem that you have this data breach. Now, multi-party computation is a paradigm from cryptography, so that's not a technology that we invented in our attic, but it's an existing field of research in cryptography. But we as a company, Roseman Labs, are a party that implements these mathematical theories in software and make it alive, make it work in practice. And in that paradigm, there is multiple computers, and in this picture, each participant runs a computer, and those computers, they interact with each other, and in such a way that they interactively do the data processing, and in such a way that the parties do not get to see each other's data. That's very much in a nutshell explained what is happening there. But then in practice, we don't apply it in that way, in the sense that not every party is interested in running its own infrastructure. So what we do, while this is kind of the traditional deployment model where every participant is running infrastructure, we typically assign a number of parties who run the infrastructure on behalf of the data ecosystem. So there can be multiple parties that just input data into this system, and then there can be also parties that just receive the result without being involved, or there can be parties who also input a result and get a result. Sorry, input data and get a result. And typically we run those computational nodes in separate cloud infrastructures. So in this model, even the cloud can also not learn the data, which is a very strong confidentiality property. So back to this topology, I now want to zoom in into the client side, and we are here at the Python conference. So here's the link back with Python, namely that the client can instruct this machine or this system what to do via a Python interface. So what we do is we mimic a pandas interface and also a sci-kit learn interface. So for the data scientist, it's a familiar API, it's a familiar interface. But in fact, maybe like Spark, you are interacting with a server-side system, right? So the computations are not happening on your own laptop or computer, but they are happening in the cloud, and in this case on multiple independent machines in the cloud that run these special cryptographic protocols. The Python package that we have built is called crandas, encrypted pandas, and here you can go to the documentation, which is online, and typically how people interact with this system is you would start with sharing a data frame, which is then encrypted and uploaded to this server cluster, so that you or another participant in this data ecosystem can then work with that data. And by the way, if you upload it, it could be that there's participants in the ecosystem that are not familiar with Python. So we also have a GUI interface, like web-based interface, where the data is encrypted in the browser. So that's an important point, that the data is encrypted before it gets to these servers in the cloud, so that the servers in the cloud never see the plain text data. So then once these data sets have been shared in encrypted form with this cluster, then you can manipulate this encrypted data. For example, here you can select various columns of some table, and you can describe the data set. So without inspecting all the values, you could maybe look at the column averages or standard deviations or what have you, assuming that that is allowed in this data ecosystem, that it is approved by this approver. And also importantly, you can join data sets. So for example, there's one party who uploads a table, and then you want to link that data to data that is coming from somewhere else, right? And for example, you could think of that you want to make a link or join on a social security number, which is typically a very sensitive piece of information. But here the advantage is that variable on which you make the join, on which you merge the tables, never has to be revealed, and even not to these computers that execute this join. So that's, again, a strong confidentiality property. So all this data that you have remains encrypted in these several servers. So then after joining, you maybe want to then use that data, that combined data set that you have obtained, and train, for example, some machine learning model on that table. So here is, for example, an example of a logistic regression model that you want to train. So you can train machine learning models on encrypted data. And then purpose binding, which I already mentioned before, that's this crucial piece where some other party in this data ecosystem can inspect what you want to do as a data scientist and either approve it or, well, not approve it. And how that works is that you record the script that you want to run, the Python script, and then offer this recorded script to the approver that can then inspect whether yeah, the actions that you're going to do on the data are in line with, for example, the law, what the law says about the data processing. And this recording mechanism is such that it kind of focuses on the relevant parts of your script, because it could be that if you do a data processing and you are done, that you are then going to locally plot that data. But this plotting is purely a local process, so that's not really relevant for the approval process. Only the part of your script where you are kind of touching these other data sets and manipulating the data that is part of the ecosystem, that is the part that is relevant for this approval process. And then also there's a strong link between approvals and execution of the query, in the sense that if you do not have the approval, also the system will not execute the query for you. And that is kind of enforced at all these servers independently. So even if you control one server and you make that server still run the query, then the other servers will not collaborate and the data will not be processed. So that's also a technically enforced purpose binding. Okay, so let me conclude this talk by giving you a real-world example that ultimately led to winning a privacy award. And the example is a Dutch public transport case, where in the Dutch law there is a special law that says that if you have a disability or you're elderly, that the government pays for your transport. And here there was a question like, would it be a good idea to give people that are eligible for this special benefit, would it be a good idea if we give them a free public transport pass? Would then they be using less the taxi service? That was a question. And this is a problem where there's many different entities involved. So, for example, the municipality has the link between the persons who are eligible for these special taxi services. But there's also, for example, the taxi service who registers which taxi rides are being made, and they link that to some number, but they don't know the person name or where that person lives. They don't have that information. So information is spread around those different parties that the logos are shown here. And that's really the instance of such a data ecosystem that I was talking about before. And well, this is a bit technical and I'm not going into the details, but by cleverly joining and performing group bys and doing kind of typical SQL operations, but then in this system where all the data remains encrypted, we were able to answer the questions that they were asking. And the questions, for example, were like, what is the number of kilometers that a traveler traveled by taxi or so. So then you have to do a group by the person, and then, the group all the taxi rides from one individual and then add the number of kilometers, etc., etc. But we could do that all, as we say, under the encryption, so without leaking any data that was not part of the result. We could just reveal the result to those queries, and the rest was visible to nobody. So that's a really strong, I would say, achievement of data minimization. Well, here was then some result that has been blurred because we couldn't show the precise data here, but you get the idea. And as I said earlier, we were awarded together with Public Transport Groningen-Drenthe the Dutch Privacy Awards of this year for this work. And I think that's nice, well, not because it's just nice to win such a prize as a company, but also that it helps to make known to the world that these technologies now exist and are practical, because they exist already for quite a while, but for a long time they were not practical. It was purely like a mathematical toy idea, but I think the last decade, computers have become more powerful, network technology has improved, and also our software implementation is mature enough so that we can do things that are relevant in practice with this technology now, and have the very strong benefits also from a GDPR perspective. I think that was my story. Thanks a lot.